everyone, Mrs. H here again. We're picking up our Chapter 7 lessons now with our third state of matter called the solid state. We realize that solids are very rigid, fixed position compounds, and we can classify them based on the organization or disorganization of their shapes. Solids can be crystalline or amorphous. Let's define the term crystalline as a solid that has a regular arrangement of particles, and those particles can either be atoms, molecules, or ions, but it has a definite repeating pattern. An amorphous solid has no regular arrangement, and they are rarer, but they're not really a regular shape at all. So amorphous means no regular arrangement, but they're still closely packed particles, as they are indeed in the solid phase. Now, in this crystalline solid, we'll notice that there are actually 4 different types of crystals. We can call ionic, we'll investigate molecular, a network solid, and a metallic solid. 4 different types of crystalline solids: ionic, molecular, network, and metallic. Let's look at each one of those. An ionic compound is composed of oppositely charged ions. And just think about table salt, sodium chloride. Sodium chloride is a definite repeating pattern. We called ionic compounds, that repeating pattern was called a formula unit. Notice that you have a repeating pattern of sodium, then chloride, then sodium, then chloride. A molecular solid is composed of individual molecules arranged regularly. This would be ice. Right? Water is a molecule. It's not a salt, right? These are salts over here. Ionic solids are called salts, and salts are composed of charged ions. But water is not a salt. It's a molecule, but it can be in the solid phase, and when it is, we call it ice, and you can definitely see a repeating crystalline structure of ice cubes. When water solidifies, there is a repeating pattern. And think about the beauty of a snowflake. A network solid is composed of a vast number of atoms covalently bonded together. And this is an example we looked at in the beginning of the chapter. Silicon dioxide, we said, was a component of sand. And notice that they are held in rich positions, and they're just held covalently bonded. Large networks of solid atoms bonded together. And the fourth was called a metallic solid. Now these aren't true, we called it a type of bond. It was a metallic bond we learned about. But it's really just a lattice of metal cations with freely floating electrons moving about. That's why a metal is such a great conductor of electricity. Copper atoms, iron atoms, tin, whatever the conductor of electricity might be, set up a metallic solid, a lattice of metal cations where the electrons are free to flow between atoms. And then we said if it wasn't crystal, it was amorphous. So a solid that's amorphous has no regular shape, and typically they're formed by accident in the lab. If you form an amorphous solid, it's a liquid that has cooled too quickly to form a regular crystalline structure. And very large covalent molecules tend to do this. Another solid that does that regularly is sulfur, is an amorphous solid. Rubber, glass, plastics are all examples of solids that have no regular arrangement to their particles. So let's practice examining these solids and tell me which type of crystalline solid is formed. Do you remember your choices? We said we could have an ionic, think salt. We could have a molecular, think that it's molecules, non-metal to non-metal. We could have a network, which, remember what we called that here? We called it a network solid. Or you could have metallic. So I'm just trying to remind us what our choices are. Calcium chloride is an ionic compound. It's composed of ions. It's composed of a calcium ion and 2 chloride ions. This is an ionic compound Therefore, it would have an ionic, remember this word here? Ionic solid right there. Iron is a metal. It's not attached to anything, so it would be a metallic. Remember this one right here from the copper example? A metallic solid. Here's sugar, C12H22O11, table sugar. Table sugar is a solid at room temperature. It's made of a molecule, so it has a molecular network. Remember this guy? Molecular solid. That would be an example of sugar. And the last one is NH3. NH3 is a molecule, so it would be a molecular solid. Another quality of solids is a physical property known as specific heat. Specific heat is defined as the amount of heat energy needed to raise the temperature of 1 gram of any substance by 1 Celsius degree. This goes back to our chapter 6 a little bit when we learned about calories and joules. Calories and joules, we said 1 calorie was the same as 4.184 joules. And we defined really the specific heat of water at that time. We said it takes 1 calorie of energy to raise 1 gram of water 1 Celsius degree. Or in the metric system, we defined it as saying it takes 4.184 joules of heat energy to raise 1 gram of water by 1 Celsius degree. I'm telling you the specific heat of water when I'm giving you that information. But every substance has its own unique value of specific heat. Just like density. Density is unique to each and individual compounds or elements. It is an intensive property that gives us the quality related to, if you remember, density is mass over volume. This is a property just like specific heat, unique to each individual compound. And the reason we're bringing it up here is we can study specific heats of metals. So specific heat, the larger the number, the value, the magnitude of the specific heat, it takes more and more and more and more energy to raise the temperature of 1 gram of a substance by 1 Celsius degree. So if I put in a little bit of heat, it doesn't move very much on the temperature scale. So if you compare, say, example 4.184 joules per gram degree Celsius is that specific heat for water. And let's say I have a metal coming in at 0.2 joules per gram degree Celsius. Adding the same amount of heat, the water hardly warms up at all, and the metal will get really hot really fast. Here are some examples of specific heat of substances. In the left column, these are all examples kind of just written out here. We have aluminum, 0.214 calories per gram Celsius. See that calorie unit? Or in the metric system, a joule per gram degree Celsius. Remember the conversion. 1 calorie is 4.184 joules per gram degree Celsius. And you can see that right here. That's the very definition of water, right? That's our base of the system. So we can just see a list of all these different substances, and the term specific heat is applied to them, telling me how many calories of energy or how many joules of energy it would require to warm up 1 gram of that substance by 1 Celsius degree. And if we want to calculate, we can consider calculations in terms of the mass, the specific heat, and the change in temperature. Let's do some thinking together. Considering the elements aluminum, copper, and gold. So just a moment ago I had this screen up, aluminum, copper, and gold. I think this is in your notepad for your convenience, but just so I didn't have to go back and forth on the slide, I wrote them down here. Aluminum, copper, gold, and here's iron, just from the table on the previous slide. Aluminum has a value of 0.214, copper 0.09, gold 0.03, and iron 0.107. Those are in calories per gram Celsius. What if you put in 10 kcals of heat to each of these elements, same amount? What element would have the highest temperature? Which one would warm the most? What do you think? Which one has the lowest specific heat? The one that doesn't take much energy at all to convince it to warm up. Looks like gold. The gold specific heat is 0.0310 calories per gram degree Celsius. So thinking about how much would it raise if I added 10 kcals? A lot. And which one would hardly move at all? Which one is the biggest specific heat number? Aluminum would be this 0.214. And again, just comparing, this is the smallest specific heat value. This is the largest specific heat value, meaning that this element, gold, would change temperature the most. Which element would require the largest amount of heat to raise it by 5 Celsius degree? And that's going to be the largest one, right? It's going to take a whole lot of energy to get aluminum because it has the highest specific heat value. The higher the specific heat, the more energy it takes to raise it by 1 Celsius degree. The larger the specific heat, the less the temperature of a substance will change when it absorbs energy. The larger the specific heat, the more heat that must be added to increase the temperature of the substance. And that's what we just wrote on that previous slide. Well, let's introduce a formula to how to calculate specific heat. We can calculate heat released or heat absorbed. Heat absorbed we know to be endothermic. Heat released is to be exothermic. Heat is measured in calories or it's measured in joules. The heat unit is a calorie. We can calculate that by taking the mass times specific heat times the change in temperature. Heat gets a letter Q for a symbol. I don't know why, but Q is given to heat. M stands for the mass measured in grams. Delta T stands for the change in temperature. And just think about what that means. You would find a change in temperature by knowing its initial and final. So T final minus T initial is how much it changed by using a thermometer. And then you're going to get the specific heat, and it's given a little letter C. The specific heat is the other variable in this equation. And that's the unit then, this could be in Celsius degrees or in Kelvin, because when you subtract, you're going to get the same difference. If I subtract two numbers on the Celsius scale, I would get the exact same answer if I had subtracted those values on the Kelvin scale. So it doesn't matter if we're in Kelvin or Celsius here. If my heat is measured in a calorie, my unit for specific heat is calorie per gram degree Celsius. If it's measured in a joule, it's joule per gram degree Celsius. So we're just matching units. Q is equal to MC delta T. That is our formula for calculating heat. I have this nice little tool that helps me remember. Draw this with me and it will help you with the algebra. Here's Q on the top, and I can find Q by multiplying M times C times delta T. And this allows me to use this little visual where I can cover up the variable that I want to solve for and see the relationship to the other. So cover up Q, just cover this up and you get M times C times delta T. If I want to solve for specific heat, cover this one up and you get Q over M times delta T. So it's just a little, a little tool, a little visual to help us remember the algebra. Q on the top is found by taking mass times specific heat times the change in temperature. Shall we try one? How many calories are needed to heat a pot of water from 25 degrees Celsius to 100 degrees Celsius? I'm going to make that bigger. Q is equal to M times C times delta T. We're being asked for calories, so this is what I want to know. That's the one I'm going to cover up. I have 1,600 grams of water, and my temperature change will be the difference from, here's your initial, here's your final. So delta T is 100 minus 25, which is 75 degrees Celsius. We'd like to know Q. Well, you know what's not given on this page, but we're expected to know it? What is the specific heat for water? Now, I know that I gave you a table, but this is one that you should really just know. Know this one. 4.184 is equivalent to saying 1 calorie. So it's 1 calorie per gram degree Celsius. That's what I have to know right here. 1.0 calorie per gram degree Celsius. So I want to know Q. I'm going to find that by multiplying M times C times delta T. 1,600 grams times 1 calorie per gram degree Celsius times our delta T, which was 75. Notice how grams canceled? Do you notice how Celsius canceled? And when we multiply M times C times delta T, you found Q. And Q comes out to be calories of energy. So we're just going to take 1,600 times 75 degrees Celsius, and we get a big number. How many zeros is on your screen? 120,000? And there's your answer. 2 sig figs? That will work. How'd you do? Shall we try another? How much energy is required to heat 28 grams of iron from 19 degrees to 150 degrees? Report your answer in calories and in joules. My formula, my little helper, Q is equal to M times C times delta T. What do we know? Well, we were given 28 grams. I can place that here. That's the mass in grams. The temperature change, initial was 19, T final was 150. So the delta T was 131 Celsius degrees. We want to know energy. That's Q. How much energy? That's heat energy. And the C, the specific heat constant. Well, again, I gave you this chart. You do not have to memorize all of these elements. Don't think that for a minute. But I do expect you to remember water because it is the basis of that whole metric system. But what I did was just kind of clip art for us iron, since it was the, I just pulled that from the chart. Now in a calorie, we'll use 0.107, and in a joule, in a second calculation, we'll have to use 0.448. So heat measured in calories we'll use 28 grams times 0.107 calories per gram degree Celsius times our change in temperature of 131 degrees Celsius. Grams canceled, Celsius canceled, and we arrived at calories. 28 times 0.107 times 131. My screen reads 392.476, and let's just make sure we give that, looks like 2 sig figs. Shall we write 390 calories? What about in joules? Q measured in joules would still have 28 grams, same mass, same temperature change, but what will be different is the specific heat. We have to make sure we grab that in a joule per gram degree Celsius, but the same temperature change. See what we've done? Grams canceled and Celsius cancels, and we're going to end with joules of energy. Let's hit that. We have 28 times 0.448 times 131. My screen reads 1643.26, but let's do that to 2 sig figs. 1600 joules. M times C times delta T are units to help us find heat energy. How about another? How much energy is released by 200 grams of water? So when we're asked to solve for energy, that's our Q. And we know that it's found by taking M times C times delta T. We're given 200 grams of water, and it's cooling from 55 to 12 degrees. So here's your initial. Here is your final. Now, final minus initial. This is going to give us a negative answer, but that's okay because it's heat releasing, exothermic. Heat releasing means we'll have a negative value for exothermic. So right here, this is negative 43 degrees Celsius. Specific heat of water in a calorie we know is 1. So we'll take 200 grams of water times its specific heat of 1 calorie per gram degree Celsius. And just in your head, remember, it takes 1 calorie of energy to raise 1 gram of water by 1 Celsius degrees. And we're letting it cool by 43 degrees Celsius. When I calculate, I get negative 8,600 calories. And the negative just simply means exothermic, heat releasing. Now I can convert that into a kilocalorie. Whoopsie. 1 kilocalorie is 1,000 calories. And so I'll just slide the decimal 3 spots to the left to convert my calorie into a kcal. And there's that answer. Not too bad, not too bad. Here's an example of using a different compound called 2-propanol. And all I did was go to your chart and I pulled off its specific heat. So now, remember, our little helpful hint here, Q is equal to M times C times delta T. And let's just fill these in as we read it. It says 400 calories of heat. That's this variable. We're given Q this time. Of 25 grams, that's a mass unit, of propanol at 21 degrees. Well, this is the initial temperature. We're being asked to solve for the final temperature. So this is what we want to know. I need to figure out how much it changes by so that then I can figure out where it will land. So 2-propanol in calories. That's this number right here. So this time we know Q is 400 calories. I want to know the specific heat. So I have 25 grams times 0.612 calorie per gram Celsius, and that's going to give me my delta T. So this is what we want. You see what we have? Q over M times C. Q over M times C. And that's going to pull out delta T. So hit that with me, your key sequence. 400 divided by parenthesis 25 times 0.612, close parenthesis. Now my screen reads 26.144. Well, just right there is fine. Now that's not my final answer. That's my delta T, how much it changed by. If we're adding heat means it's going to warm up. And think about that. If the initial temperature started at 21 degrees and it warms up by 26 degrees, I'm going to keep the 2 sig figs we need anyway. Right? Added to means it's going to warm up to the final temperature. Right? This will be a bigger number because I'm warming it. So it's going to land at 47 degrees Celsius. It changed by 26 degrees Celsius, so it would end at 47. We're taking the initial and adding the change to find the final. Think about what I just said there. TF minus TI is delta T. So if you just think about what we said, you're going to just rearrange that and say to find the final, it's delta T plus the initial. And that's how we found 47 degrees Celsius. Pause and think this through. Give yourself a little think time and try this problem out. Come back to me when ready. We have 2 separate problems here, don't we? We have to solve for copper and then for mercury. I know that Q is equal to M times C times delta T. We want to know the final temperature, so we better solve for delta T. That's what we want to know. Now both of these are giving me 20 calories of heat, and they're both giving me 10 grams, but I've got to solve 2 separate problems. One using the copper and one using mercury. So let's set up for copper first. With copper's value of 0.09, this looks like my math. Delta T will be solved for by taking our 20 calories and placing it over our 10 grams times the specific heat of 0.09 calorie per gram Celsius. This is your Q, this is your M times C, and you're solving for delta T, right? This is the one you want, so you cover it up and you see the algebra, Q over M times C. So let me hit that for us. We'll have 20 divided by parenthesis 10 times 0.09. And I hit and it says 22.22 degrees Celsius. Now, if it started at 15 degrees Celsius and you added heat, the new temperature will be 22.22 degrees higher than 15. So I'm going to just add those two together, and the final thermometer will be 37.22. I'll just leave, that's close enough, 37 degrees Celsius for copper. What about for mercury? Its delta T would use the same 20 calories, the 10 grams that you had, but now remember mercury has a different specific heat, so 0.0335 calorie per gram degree Celsius. Remember that in a parenthesis down there. Remember, we want to solve for temperature, so you see your formula, Q over M times C. 20 calories divided by parenthesis 10 times 0.0335. And this time the delta T came out to 59.7 degrees. If the initial temperature was 15 degrees, the final temperature is simply adding those together. So while I have 59.7 on my screen, I'll just add 15, and this would end at 74.7 degrees Celsius. So clearly the mercury warmed up significantly compared to the copper. When liquids and solids change phase, or when liquids to gases change phase, energy is involved. Let's consider in this next portion of our lesson energy associated with phase changes. We know that when a solid converts to a liquid, it's called melting. And that when liquid converts to a solid, it's called freezing. These are phase changes. Notice that we have to overcome intermolecular attractions for a solid to melt. And we have to organize molecules when liquids go to solids. So think about the process in the forward direction. For a solid to turn to a liquid, it's going to require heat. So this is what we refer to as an endothermic process. When a liquid turns to a solid, it has to release that excess heat. And in doing so, that is an exothermic process. How much energy in calories is absorbed when 50 grams of ice cubes melt? Now, the heat of fusion, did I define that? That's down here, sorry. Let me back up and make sure you got that in your notepad. The heat of fusion, it's defined as the amount of energy needed to melt 1 gram of a substance. I'm not warming it up, I'm not cooling it down, because melting points and boiling points are constant, but we're changing phase, and that's what the energy is being used for, the heat of fusion. How much energy is needed to melt 1 gram of any substance is known as its heat of fusion. So now that I've defined that term, heat of fusion, we can use that to do a simple conversion. If I start with 50 grams of ice cubes, and it takes 79.7 calories to melt every 1 gram of ice cubes, how much energy is going to be required? See how it's just a simple conversion? If 50 grams of ice times 79.7 calories per gram, it would require 39.85 calories of energy to melt 50 grams of ice. I don't know why I made the calories float. So thinking about sig figs, maybe we want to round that to 3990 to have 3 sig figs. So see how I just used it as a conversion? If 1 gram requires 79.7 calories to melt, 50 grams would require 50 times as much energy. And these heat of fusion problems, 79.7 calories per gram, you do not need to memorize. It's going to be one of those given numbers, no need to memorize. But what we can use it is to recognize if heat is being absorbed or released during phase change. I want you to recognize the word released, meaning exo, so your energy should be negative. And if you read absorbed, recognize that as endo, so your energy should be positive when you calculate it. Let me model letter A. It takes 50 grams of water, and we're going to freeze it. So our phase changes from liquid to solid. And in doing so, we said it releases heat, that it's an exothermic process. So the heat of fusion, remember, is defined as how much energy it takes to melt. But here, this is the opposite problem. We're freezing. So when you think about the heat, and how about if we just say of freezing, it's going to be negative 79.7 cals per gram. And think of fusion as the opposite direction, and that's when water is melting. So that would be melting. And that's when we have a positive sign there. So 50 grams of liquid water is going to release 79.7 calories of energy for every 1 gram. And now I can see that it's going to be negative. It's an exothermic process. 50 times negative 79.7. I just did that one a moment ago. The negative is telling us that heat is being released. It's an exothermic process. In B, this time we're taking 35 grams of water and it's absorbing heat. So I want you to put that in as a positive 79.7 cal to make sure you understand that absorbing is an endothermic process. And I'll let you know that an endo is always a positive energy. 35 times 79.7. That's too big. I hit it wrong. 35 times 79.7. And that gives us 2789.5. Well, let's just put that into 3 sig figs. How about 2790? And that's a positive. This should have 3 sig figs as well, I suppose. Letter C. How much energy in a kcal, kilocalories, absorbed, positive number, when 35 grams of water melts? Well, didn't we just do that? 35 grams of water melting. All we have to do is take this and convert it to a kcal. That's easy enough. There's no difference between B and C, except we're going to end it into a kcal. So that's just taking our 2790 calories and knowing that a kcal represents 1,000 calories. That kilo is 1,000. So just move your decimal over 3 spots and you get 2.79, and that's why 3 sig figs. I have to have an answer with the same number of sig figs. So that's 2.79 kcals. And letter D, well, this is a little interesting. It gives us moles. I know that 1 mole of water weighs 18 grams. That's its molar mass. So 18 is adding 2 H's and an O. That's where the 18 is coming from. It's the molar mass. So when they said 1 mole, it's equivalent to saying 18 grams of water. And what are we doing? We're absorbing. So that's a positive number, 18 grams. 79.7 calories per gram are necessary to cause that phase change. So 79.7 times 18. And now my screen reads 1434.6 calories. I know these are positive because they're absorbing energy. Let's get that to 3 sig figs, shall we? 1430, positive for absorbing, endothermic. And the unit there is a calorie. Good work. Well, how about if we're going from liquid to gas or gas to liquid? These are called vaporization. To go from a liquid to a gas is going to absorb energy. It takes heat to cause a liquid to turn to a gas. That means that it's endothermic, positive for delta H, our heat of reaction. And if I'm releasing heat, I have the gas going back to the liquid phase. That's condensation, and that's going to be heat releasing, exothermic. The term for this is called heat of vaporization. Just like we had heat of fusion from solid to liquid, we have heat of vaporization from liquid to gas. So these are really the same type of problems. We just have a different heat of fusion versus heat of vaporization value to use. How many kilocalories are absorbed? Okay, absorbed, positive energy, endothermic. 22 grams of 2-propanol evaporates after being rubbed on the skin. The heat of vaporization of 2-propanol is given to us. No need to memorize those. It's given as 159 cal per gram. These are just simple conversions. 22 grams of our substance, and each gram requires 159 calories. And so that just cancels the unit of gram on the bottom. And I know it's going to be a positive answer because it's endothermic. So 22 times 159 would give me a value of positive 3498 calories. And then to get the kcal, I'll just divide by 1,000 and slide my decimal over 3 spots. And we get 3.498. And I should probably round to 3 sig figs. 498 is really... There's 3 sig figs, and the answer there comes out in a kcal. And I know it's positive because of the word clue saying heat is absorbed, making it endothermic. You have a practice problem here, same idea. Take a little think time and work these through and come back when you're ready to check. Think through, then check. In letter A, we had 42 grams. Heat is being absorbed, so I know it's endothermic. The value of heat of vaporization for water is given as 540 calories per gram. So I'm simply multiplying 42 by 540. On my screen, it says 22680 calories. Let's give that to 2 sig figs. How about B? This is being released, so negative. Same amount of energy, it's just the opposite process. So just to kind of clarify, all that does is change the sign on your conversion factor. Heat is being released, so you end up with negative 22680 calories to represent exothermic. So I'll just take that as negative 2300 calories. Remember, endo is positive, exo is negative for heat releasing. Letter C, given 1 mole of water, it's absorbing, so I know it's positive. 1 mole of water, we just worked that out a moment ago with its molar mass of 18, converts grams, so we have 18 grams, and then 540 calories for every gram. So see what we've done? Moles canceled, grams canceled. We did a mole map conversion right in the middle there. 18 grams times 540 shows us 9720 endothermic calories. We want kcals. So just slide your decimal over. 9.72 kcals. And I'll just put that positive sign there to remind you that it's endothermic. And in letter D, well, instead of starting with 1 mole, we have 3.5 moles of water. Same molar mass though, right? Water has a formula weight of 18 grams, 2 H's added to an O. And so the only difference now is starting with 3.5 instead of 1. 3.5 times 18 times 540. And my screen reads 34020 calories, and it's absorbing, so we're positive. I do want to get that to kcals. So just divide that, move your decimal 3 spots over, 34.02, 34.0 kcals. Easy enough. Very simple conversions in this section. Almost as fun as Dalton's Law. Those were very easy addition problems. And then kind of our last topic, putting it all together, is looking at energy and phase changes on a graph. Converting a solid into a gaseous phase. We have some vocabulary. Going from a solid directly to the gaseous phase is known as sublimation. Dry ice is a great example of sublimation. Or going from a gas directly back to the solid phase, that's called deposition. We should know those vocabulary words as well. Deposition, going from gas to solid directly. There is no in between stopping at the liquid phase. If you go from solid to gas directly, no stopping at the liquid phase, that's known as sublimation. Dry ice is solid carbon dioxide turning instantly into gaseous carbon dioxide without going through the liquid phase. And so here's just a nice opportunity to tell yourself as you fill in this chart the process of phase changing and the energy associated with it. When solids turn to liquids, we call it melting. It requires energy. When liquids turn back to solids, it's called freezing, and it releases energy. When a liquid turns to a gas, it vaporizes. It absorbs energy. And the opposite of that would be condensation and releasing energy. To sublime is going from solid to gas directly, and deposition, to deposit, is going gas to solid directly. And these phase changes can be represented, and if you need to pause the video, please do so, but I'm just going to show these on a graph. And this is where I would say know these terms on a graph. Down here, below the melting point, we're in the solid phase. Solids are very highly organized, aren't they? And as I add energy, the solid will warm up until it reaches its melting point. And when it does so, notice that the energy being put into the system is being used to melt. So this is a plateau. So here we have an MC delta T problem, right? So when the energy that we're adding is actually being used to change the temperature. When we have a slope of the line, so let's say if the slope of the line is positive, as line segment AB is, line segment, so A to B, notice has a positive slope. Notice that C to D has a positive slope. and line segment E, let's say that's F, line segment EF has a positive slope. All the energy being put into the system to warm it up. So if this is representing water, I can add energy to warm up the solid ice until I reach a plateau. Now notice that at plateaus, where I have no slope of the line, it's just a flat line, I'll call that a plateau. This is where we have phase changes occurring. It's a flat line, as in line segment BC. Line segment BC is a flat line. Line segment DE is a flat line. All of the energy being put into the system now is being used to change phase. Do you notice this is an endothermic graph? That heat is being added. I'm climbing up the temperature scale. This is an endothermic, meaning heat is being absorbed through this entire graph. I'm warming up. That requires heat. Then I melt. Then I warm up the liquid phase, and then I boil, and then I warm up the gaseous phase. So all of those line segments are presented in an endothermic process. As solids turn to liquids, liquids turn to gases. Now on the opposite of that, you would have a cooling curve. But we still have some interesting slopes and some interesting plateaus. So here, of course, is a cooling curve. This is an exothermic graph. The highest energy state is a gaseous phase. When it condenses, it releases energy to form a liquid. And when a liquid releases energy, it forms a solid. This entire cooling curve releases energy known as an exothermic process. Heat being removed from the system forces a gas to turn to a liquid called condensation. And when a liquid turns to a solid, we called that freezing. So we have slopes of the line in these segments here, where all of the energy being put into the system is causing a change of temperature. But we also have these plateaus, and on the plateaus, that's where we see the energy being taken out of the system, I should say. It's leaving the system, exothermic. It's doing so to change phase. Heating and cooling curves give us a nice visual of energy needed or energy removed to change phases. Let's try a problem we put all together. How much energy is required to heat 25 grams of water from 25 degrees Celsius to a gas at its boiling point at 100 degrees Celsius? Now, let's just think of what we said. Are we warming or cooling? We're going from 25 degrees Celsius up to 100 degrees Celsius. So this is definitely a heating curve. So that means this is an endothermic process. I'm starting at 25 degrees and I'm climbing up to 100 degrees Celsius. And when I do so, going from 25 to 100, all of that energy is being used to change the temperature. That's an MC delta T line segment. I'll call that line segment AB. That the energy being used into that system is causing the water to warm up. Then something magical happens at 100 degrees Celsius, doesn't it? We change phase, and that's the plateau, right? The plateau is when the liquid will turn to a gas, and I'll call that line segment BC. We need to find the total heat involved in this warming up of water and changing its phase. Let's calculate line segment AB first. It has a slope of the line, doesn't it? So that's going to be an MC delta T problem. The mass of the water was given as 25 degrees Celsius. 25 grams, the mass in a gram. We're given the specific heat, although you should probably know it. The specific heat is 1 calorie per gram degree Celsius. And how much did the change of temperature occur? Remember that delta T is defined as T initial, T final minus initial. And so if it landed at 100 and started at 25, it changed by 75 degrees Celsius. To climb up from point A to B, we climbed 75 units on the number line. So let's solve for MC delta T, line segment AB. 25 grams times our specific heat of 1 times 75. That's 1875 calories of energy absorbed. Positive to let us know it's absorbing heat. Now what's happening on line segment B to C? Right, so here we were warming. Here is a process called evaporation, right? Going from liquid to gas. It's a phase change. So here we're going to use the heat of vaporization given to us as 540 calories per gram. So let's take our mass times the heat of vaporization. And all that means is it takes 25 grams multiplied by 540 cals per gram, and we'll solve for the heat required to vaporize 25 grams of liquid water. 25 times 540 is 13,500. Again, a heat absorbing process. So the total energy is going to be the sum of those two line segments. 13,500 plus 1875 gives me a sum of 15,375 calories. We should probably give that to 3 sig fig, so let's round that to 15400 calories. We added the two line segments together. First we warmed it up and then we vaporized. Two processes occurred. That's a lot of thinking. I'm going to encourage you to try one on your own and think this through and come back when you're ready. Please pause, give yourself think time, and then come back. All right. How much energy in calories is released? Okay, so this is an exothermic process. I like to draw my graph so I can get an idea of line segments. We have 50 grams of water is cooled from 25 degrees. That's my starting temperature. And it's going to cool to 0 degrees. Okay, and then it freezes. So we have a line segment and where we cool the water. And because we have a slope of the line, we know it's going to be a change of temperature, an MC delta T. And then at 0 degrees, we have a phase change, don't we? We're going from liquid to solid. Let's call this line segment A to B, and then line segment B to C. So we have two processes occurring. In line segment AB, we're cooling. So that just means because there's a slope of the line, we know it's an MC delta T problem. We had 50 grams of water times the specific heat of water, which is 1 calorie per gram degree Celsius. And how much did the temperature change by? Well, T final is 0 was 25, so it lowered by 25 degrees Celsius. And that's just going to remind us that heat is being released, so it's going to come out as negative heat releasing exothermic. What's 5 times negative 25? Is it 50? 50 times negative 25, and that's 1250 calories of heat being released. Now, in line segment BC, we're going to freeze. It's a change of phase, a plateau. And the heat of fusion of water is given to us. So here we're going to multiply mass times heat of fusion. And that's just a simple conversion telling us that 50 grams of water times 79.7 calories per gram. Make sure you notice that it's negative because heat is being released. So 50 times negative 79.7 is 3985. So what is the total amount of energy that's going to be released? Let's sum these two negative numbers. And when I did that, my screen reads negative 5235 calories of energy. How about sig figs? 2 of them probably, right? So negative 5200 calories. Whew, that was a good one. Heat releasing in a cooling curve, and we did a heat absorbing in a warming curve. I'm going to try one more. This one I pulled from your homework, so this one we might as well do together as well. I like to do a graph so I can see how many line segments are involved. We're going to melt 25 grams of ice. So, all right, heat is being required. I know it's endothermic, so it's going to be a positive slope. So I'm starting at ice, and it's at 0 degrees. So here I'm going to just draw 0 degrees. And I'm going to warm it up all the way to 100 degrees. Now, I'm starting at the solid phase at 0 degrees. So my first line segment is actually going to cause this to melt. So let's say from point A to B, this is the solid turning to the liquid phase. That's called melting. And to melt, it's going to require energy, but not an MC delta T problem because it's a plateau on the line. There's no slope of the line. Then all the energy that's going to be put into the system is going to warm the liquid water. And I'll call that point C at 100 degrees. So line segment AB, we're going to call that melting. Line segment B to C is warming liquid water. But then it says we've got to go all the way to turn it to steam. So we can't end at line C. We got to go from liquid to gas. And so there'll be a next step where we're vaporizing. This particular problem will involve 3 line segments. So wherever we have a slope of the line, we know it's MC delta T, but where we have a plateau, we use the mass times the heat of fusion for solids or heat of vaporization for the liquid. So here's our first step. In line segment AB, 25 grams of ice needs to melt. And in doing so, we know to melt will require 79.7 calories for every gram. So in melting, it will require 25 grams times 79.7. And I think I'll leave all my decimals here until the very end and then consider sig figs at the end. So notice here, this was what we called heat of fusion. And that's where I got my value of 79.7 grams. Now we have a slope of the line, so we're going to use an MC delta T problem. We have 25 grams of water. Specific heat of water is 1 calorie per gram degree Celsius. And what about the temperature change to go all the way from 0 up to 100 degrees? TF minus T initial gives me a change of 100 degrees Celsius. I moved 100 units to go from 0 to 100 on the number line. So 25 times 100 is 2,500 calories. And again, these are all endothermic processes. Now to go over here, line C to line D, this is vaporization. And so now my 25 grams is going to be multiplied by the heat of vaporization value of 540 cals per gram. 25 times 540 is 13,500 calories. So what's the total? I've got to add all three of those together. 1992.5 plus 2,500 plus 13,500 gives me a total of 17,992.5. Let's get that to 3 sig figs. Ooh, we've got to round 79 up, don't we? 100 and, oh, this one's tough. This is the number I need to round, which is going to be creating 180, which means I need a scientific notation. One, two, three, four. That's the same magnitude, but with 3 sig figs rounded properly. 17,992 rounded to 3 sig figs is 1.8 times 10 to the 4th calorie. You're going to take some time to process this. And I think we've done it. You've reached the end. Oh my goodness, I'm so proud of you. You need some time to practice, practice, practice. You've got a lot of formulas to practice, working to memorize things from PV over NT equal R. What are those R constants? Got to memorize them. How about Q equal MC delta T? Got to memorize that. You've got to really work. And the only way to get proficient is by practicing. Chemistry is not a spectator sport. All right, that's enough. I'll be quiet now and let you get off to practice.